Welcome back to the Deep Dive. We're here again to break down complex ideas into, well, hopefully some essential insights for you.
Glad to be here.
Today we're looking at another fascinating entry from the OEIS, the Online Encyclopedia of Integer Sequences. It's sequence A000279. Now, this one should be particularly interesting for number theory students. The formal description is, let me see, card matching coefficients Bn1 of t in the reduced hit polynomial and ANT. Okay, that sounds dense. Let's unpack that a bit.
It does sound a bit much, but what's really fascinating, I think, is how it connects these, abstract combinatorial ideas to something pretty relatable, like card matching.
Right.
And the sequence itself starts off, well, the numbers get big fast. It starts 3, then 24, 216, 1824, 1824, 5150. It just keeps climbing very quickly.
Okay, 3, 24, 216. So let's get right to the heart of it. What is A000279 actually counting for us? What problem are we solving here?
So at its core, it's counting permutations, but very specific ones. Imagine you have 3 different letters. Let's just say A, B, and C. And for each letter, you have n copies. So if n is, say, 5, you'd have 5 A's, 5 B's, and 5 C's.
Right, 15 letters total.
Exactly. And A000279 counts the number of ways you can arrange all those 15 letters so that there's exactly one fixed point.
Exactly one fixed point. That sounds very precise. Can you maybe clarify what a fixed point means here, especially with these copies involved?
Yeah, absolutely. So a fixed point in this context means that after you've arranged all, say, 15 of those letters, only one single letter ends up in a position that sort of matches its original type.
So like if an A was meant to be in the first group of positions and one A ends up there.
Precisely. But, and this is the crucial part, only one such match happens across all 15 positions. Every other letter, all the other 14 letters, must be in a position that doesn't match their type.
I see. So for N5, that fifth term you mentioned, 15,150, that's telling us there are over 15,000 ways to arrange those 15 letters where only one single letter is in a correct spot type-wise?
Exactly that. It's a very specific condition.
That number, 15,150, it already sounds pretty big for just N5. Why is it that specific number? And how does the sequence behave generally? Does it just grow steadily, or is it more dramatic?
Well, that specificity comes from the strict rules of combinatorics counting things precisely. It's actually a pattern you see when you want almost complete derangement, but, with just one anchor point.
Okay.
And as for growth, it's not steady at all. It's remarkably rapid. It grows roughly exponentially. The approximation is something like 8 to the power of n, multiplied by a constant, the square root of 3 over pi, which is about 0.5513.
Wow, 8 to the n.
Yeah. So it really shoots up. By the time n is 10, the value is already huge, in the tens of millions. It's like the letters are almost perfectly shuffled, except for that one single exception.
That exponential growth is pretty amazing. So what kind of math is working behind the scenes here? This is where it gets really interesting for the number theory folks listening.
Right. The mathematics underpinning it is quite rich. The formal description mentioned reduced hit polynomials. You can think of hit polynomials generally as tools that count how many things land back in their original spots after some rearrangement. The reduced part here specifically honed in on the case where exactly one thing hits its original spot. That's what A000279 is counting.
Oh, okay.
There's a formal summation formula, too, involving binomial coefficients. It looks like AN equals 3n times the sum of Cn, k plus 1, times Cnk times Cn1k for k from 0 to n1.
Okay, that looks complicated on paper.
It does, but it's essentially a precise recipe for counting just those arrangements with a single fixed point. And beyond that, it connects to more advanced things like hypergeometric functions through its generating function.
Hypergeometric functions,
Yeah.
right. That puts it in a broader mathematical context.
Exactly. It links it to a powerful class of series that pop up in all sorts of areas, physics, probability, you name it.
Okay, so we've got the definition, the growth, the underlying math.
Yeah.
But let's bring it back to the ground. For our listeners, beyond the theory, where might these ideas of specific permutations and fixed points actually be useful?
Well, it's a classic combinatorial sequence, so its roots are deep in permutation theory itself. That has broad applications. For number theory students, think about fields like, say, cryptography.
Okay.
You might want systems that thoroughly scramble data, making it look random, but maybe you need one specific known reference point left unchanged for validation or integrity checks. That's sort of analogous.
I see the connection.
Or maybe in network analysis, modeling communication paths, you might be interested in permutations where nearly all connections are rerouted, except for one specific critical link. The sequence itself draws on foundational work like Riordan's book from the 50s on combinatorial analysis and, of course, Sloan's OEIS itself. It's well established.
So quite a journey then into A000279. We started with card matching, found the sequence counting very specific permutations with just one fixed point, saw its explosive growth, and touched on the sophisticated math behind it.
Absolutely. It really underscores how these sequences in the OEIS, which might seem abstract at first glance, can actually model tangible scenarios and require some pretty powerful mathematical tools to understand fully.
It really does. And it leaves us with maybe a thought to ponder. How many other complex patterns are hidden away in these sequences, just waiting for us to find the right lens, the right question, to reveal their practical side?
A question worth asking.
Indeed. Keep exploring the OEIS, everyone, and we'll catch you on the next deep dive.